Hello students, let us start the ITC class. Yesterday we were discussing this binary erasure channel. I will show you the picture once again. You can see this binary erasure channel where at the destination there is another third symbol, and you can see that y1 is received only when x1 is transmitted, y2 is received when the x2 is transmitted, y1 and y2 will not be received on the other hand, which means y1 is not received when the x2 is transmitted and y2 is not received when the x1 is transmitted. Instead, y gets received. Now, such channel is called erasure channel, means the channel can find out that the symbol obtained is not present in the defined alphabet set, and we can use a method called ARQ. I was telling you yesterday, we can use a method called ARQ, automatic repeat request, by means of a reverse channel. So such channel is called binary erasure channel because the error is totally erased. But the disadvantage is the requirement of the reverse channel. Now this was the noise matrix or the channel matrix which we had written yesterday. Y1 is received when x1 is transmitted, that is P. Similarly, y2 is received when x2 is transmitted, that is P. Otherwise, whenever there is an error, y is received, so that is 1 minus P and 1 minus P. This is the noise matrix now. Now, this matrix is different from all the earlier matrices which we had seen. Now, in the other earlier matrices, it was easy to write the channel matrix. Later on, it was easy to write the JPM also. It will not be the case in this case of a channel. Let us see how it is going to happen now. So, as this is also a symmetric channel, h of y slash x is p into Lg of 1 over p plus 1 minus p into Lg of 1 over 1 minus p. You can see this is also a symmetric channel. The elements which are there in one row are also there in the other row, but at different columns. So, this is a symmetric channel. So, we can write h of y slash x equals p of Lg of 1 by p plus 1 minus p Lg of 1 by 1 minus p. This cannot be used for obtaining the mutual information. Why? H of y involves this y also, means along with y1 and y2, there is this erratic symbol also. And we definitely know that this is corresponding to error. But this y is getting rejected to the receiver itself. Receiver is intelligent to identify which one is the defined alphabet set and which one is not. That is how this is called erasure channel. So h of y involves y, but which is rejected to the receiver. So this particular equivocation cannot be used to obtain the mutual information now. So I of x semicolon y is h of x minus h of x slash y. Let us derive how to obtain the mutual information now for the BEC. So, let p of x1 equals small m and p of x2 is naturally 1 minus m. So, h of x is m into Lg of 1 over m plus 1 minus m Lg of 1 over 1 minus m, because at the source we have only two symbols. Now, the JPM can be written based on this data in this manner. P of x comma y is p into m 1 minus p into m 0 0 1 minus p into 1 minus m p into 1 minus m. This way we have obtained the JPM for the binary erasure channel. Now, p of y1 is p into m, p of y is 1 minus p, p of y2 is p into 1 minus m. From the joint probability matrix itself, we have obtained the probabilities for all the three symbols. So, this is p into m plus 0, this is 0 plus p into 1 minus m, 1 minus p into m plus 1 minus p into 1 minus m. So, that way we get p of y equals 1 minus p itself. Now, from the Bayes theorem, we know that p of xi slash yj equals p of xi comma yj divided by P of Yj. This P of xi comma yj is nothing but P of yj slash xi into P of xi. So that way, from the base theorem, now we obtain P of x slash y, that is 1 m 0 0 1 minus m 1. This is using the base theorem again. Now we have equivocation from the other side. So h of x slash y equals summation of I equals 1 to 2 and summation of j equals 1 to 3, because we have 2 source symbols and 3 destination symbols. P of xi comma yj lg of 1 over P of xi slash yj. That way we can find out the equivocation. This is nothing but P into m into Lg of 1 plus 1 minus P into m into Lg of 1 by m plus 0 plus 1 minus P into 1 minus m into Lg of 1 by 1 minus m plus P into 1 minus m into Lg of 1, using all these summations. So in this manner, we simplify this. We get 1 minus P into m into Lg of 1 by m plus 1 minus P into 1 minus m into Lg of 1 by 1 minus m. That way, we simplify this expression. Finally, h of x slash y equals 1 minus P into m into Lg of 1 by m plus 1 minus m into Lg of 1 by 1 minus m. That let us call it as equation number 2. Now, from 1 we have h of x slash y equals 1 minus P into h of x from the equation 1. Let me show you the equation 1 here again. So, from this equation 1, we have this h of x slash y equals 1 minus P into h of x, or now I can write as mutual information I of x semicolon y equals h of x minus 1 minus P into h of x, or mutual information I of x semicolon y equals small p into h of x. That way, we have obtained an expression for the binary erasure channel. So now, the channel capacity of binary erasure channel is given by C equals maximum of mutual information, that is nothing but maximum of P into h of x, that is P into maximum of h of x. That maximum of h of x is nothing but Lg of 2, because we have only 2 source symbols. So that way, the channel capacity of the binary erasure channel is the probability of that source symbol itself. Okay. So C equals P, where we had defined P as, what is this, y1 slash x1, y2 slash x2. I will show you the picture once again. y1 slash x1 was P, y2 slash x2 is P itself. So finally, we obtain the channel capacity of the binary erasure channel is equivalent to the conditional probability of the particular channel itself. That was the third channel which we discussed. Now let us discuss the fourth channel, that is called as noiseless channel. If the channel matrix contains only one non-zero element in every column, then that channel is called as noiseless channel. This briefly we had discussed earlier also. You can see an example. P of B slash A equals, you have this A1, A2, A3, and you have this B1, B2, B3 up to B6. That means we have 6 destination symbols and we have 3 source symbols. Now you can see that there is only one non-zero element in each column. Means B1 is received when A1 is transmitted. B1 is not received when A2 and A3 are transmitted. Similarly, B2 is received when A1 is transmitted. B2 is not received when A2 and A3 are transmitted. That way, for a given destination symbol, there is only one particular source symbol that way. That means each column has only single non-zero element. Now such channel is called noiseless channel. On the contrary, the other type is called as deterministic channel. We will see that later. So this is called as a noiseless channel, which simply means that only one destination symbol is obtained for the transmission of the source symbols, which means we can say the channel is not introducing any noise as such. Okay. You don't have to worry about whether B1 is received when A1 is transmitted, B2 has to be received when A2 is transmitted, B3 has to be received when A3 has to be transmitted. You don't have to worry that way, because in this the source symbol alphabets are 6, whereas the destination symbol alphabets are 6, whereas the source symbol alphabets are only 3. So we don't have to have a specific relationships defined. Now anyhow, it is called as noiseless channel, which is indicated by this matrix, where we know that distinctly only one symbol is received at the destination. That's all. Let us have an exercise now. Prove that the channel matrix shown above corresponds to a noiseless channel and find its channel capacity. Now how do we prove that this particular channel is a noiseless channel? Just by your observation, we can come to know that this channel is noiseless. We know that only one symbol is received at a time at the destination. But how do we mathematically prove this is the question. Let us try to prove this mathematically. Now, for the given channel matrix, the input conditional probability matrix or PA/B can be written like this. P of A/B, we can write it as A1, A2, A3. Again, we can write 1, 1, 1, 1, 1, 1 this way. Because anyhow, it is a noiseless channel, right? So there should be only one particular symbol received when a source symbol is transmitted. That is what we have here, right? This can be half, half, 3, 5, 3, 5, all that. But we can write it this way as a conditional probability matrix. Now, when we write it this way, H of A/B is summation of I equals 1 to 3, J equals 1 to 6 for the source symbols as well as the destination symbols. P of A, Bj into Lg of 1 over Pa of A/Bj. Now, let us compute this. Summation of I equals 1 to 3, J equals 1 to 6 of P of Bj into P of A/Bj. That is what is the joint probability into Lg of 1 over P of A/Bj. Now, this is equivalent to 0. Why? Lg of 1 over n is going to be 0. Now, this is Lg of 1 over 1. Everywhere we have 1, right? Lg of 1 over P of A/Bj. Now, this term is going to be 0. When this term is going to be 0, the whole thing is going to be 0. That means the conditional entropy is 0. Which means what? Which means the mutual information is H of A minus 0. That is H of A itself. That means all the source entropy is transmitted to the destination, and that is where it is becoming a mutual information, which simply means that the two circles are merging. Please recall that particular diagram where we had shown two circles with the overlap. Now the two circles are merging. Therefore, the channel capacity is maximum of mutual information. In this case, we have H of A maximum. It is nothing but Lg of M. This we already know. This is the number of source symbols. So the channel capacity for this given noiseless channel is 1.585 bits per message symbol. So this is how we are mathematically proving that this particular channel is actually a noiseless channel. Now let us come to the fifth one, that is the counterpart of the noiseless channel, that is called as deterministic channel. If the channel matrix contains only one non-zero element in every row, then that channel is called as the deterministic channel. This is the counterpart of the noiseless channel. Here you can see that B1 is received when A1 is transmitted, B1 is received when A2 is transmitted. Okay, but look at the row. At the row, it is either B1 received or B2 received or B3 received. B1 is received only when A1 and A2 are transmitted. Okay, B2 is received when A3, A4, A5 are transmitted. B3 is received when A6 is transmitted. So there is only one non-zero element in every row. Okay, now this is called as deterministic. In the sense, we will be receiving a particular symbol at the destination for some set of symbols which are transmitted at the row, at the source. Okay. Let us proceed. Now this is the deterministic channel. Let us have an exercise. Obtain the channel capacity for the deterministic channel which is given above. Proceeding with the same methodology which we proceeded for the noiseless channel, h of b slash a equals summation of I equals 1 to 6 into summation of j equals 1 to 3, because here the source symbols are 6 in number and destination symbols are 3 in number. P of a comma bj, Lg of 1 over P of bj slash ai. We can again split it. Summation of I equals 1 to 6, summation of j equals 1 to 3, P of ai into P of bj slash ai, Lg of 1 over P of bj slash ai. Now in this case also it is 1 only, right? We have that unity only. So again we will get 0 only. Now mutual information I of a semicolon b equals h of b minus h of b slash a. This is equal to h of b, which means what? In case of a noiseless channel, we had the mutual information which was the entropy of the source. Here in case of deterministic channel, we are getting mutual information, that is the entropy of the destination. Obviously it has to be so, because both are counterparts of each other. So in the case of a noiseless channel, we came to know that all the source information is available at the receiver, right? But here we know that all the destination information is available there. That is why this is a deterministic one, which is a counterpart of the noiseless channel. So now the channel capacity is h of b maximum, that is again Lg of 3, that is 1.585 bits per message symbol. This is as same as the earlier one. So we have seen till now totally 5 types of channels, and we have seen both for noiseless channel and the deterministic channel, the channel capacity remaining the same for this particular given example. Now let us come to the 6th concept called cascaded channels. We can have 2 channels cascaded like this. We can have source X, destination Z, in between one intermediate node called Y, or intermediate communication part which can be called as Y. Now this Y is the destination for X, but Y is the source for Z. We can have many such combinations in our communication systems. In fact, we have, I gave you an example of switches and routers, and I gave an example of the OS model in the last class. There can be many communication parts or subparts that are in between the source and the destination. Now I am the source, you are the destination. In between us, we have many machines now, many intelligent communication machines. They are processing data also, they are transmitting data also, they are storing data to some extent. So now we can say that in between you and me, the cascaded channels are existing. Now from my laptop to the nearest switch in the lab, there is one channel. From the switch to the router, there is a channel. From the router to the backbone network, that is a channel now. From the backbone network to your side's router, or from your side's router to your side's switch, if you are connected in the same way as I am connected here. So this way, there can be many cascades now, not just 1 or 2 cascades. 2 participants are waiting in the lobby and I am admitting them. Okay, there can be many such channels. Now let us see, this is an interesting thing where till now we were worrying only about the source and the destination. But now there are channels that are connected in series. Let us see what is going to happen now. Actually, we will have more issues now compared to whatever issues we had till now. Anyway, let us see. Now, when these two channels are cascaded, I of x semicolon y is h of y minus h of y slash x. I of y semicolon z is h of z minus h of z slash y, because now we have two channels. So, I of x semicolon z is h of z minus h of z slash x. But how do we find out h of z slash x? We can find out h of y slash x. We can find out h of z slash y. How do we find out h of z slash x? Let us see. Now obviously, I of x semicolon z is less than I of x semicolon y. Why? Just look at this. I of x semicolon z is less than I of x semicolon y. Means the mutual information received at z is obviously less than the mutual information that is received at y. Why? Because channel 2 will have an added noise in addition to the noise that was added at channel 1. That is obvious. We are not dealing with the ideal channels here. We are not dealing with the purely noiseless channels or the purely deterministic channels also. Actually, those two channels are supposed to be ideal channels. We are not dealing with the ideal channels at all. We are dealing with the practical channels. So, in such a way, obviously, I of x semicolon z is less than I of x semicolon y. That is the outcome of the cascaded channel. Let us have a case study now for the cascaded channels. We will be considering the binary symmetric channel only. Let us have a cascading of two binary symmetric channels. So you can see here x1, y1, there is this small p, x2, y2, there is this small p, and we have y1 slash x2 is 1 minus p, y2 slash x1 is 1 minus p. Now again, from y1 till z1, let us say we have p, and again from y2 till z2, let us we have p. Obviously z1 slash y2 is 1 minus p, z2 slash y1 is 1 minus p. This way, right now we have two cascaded binary symmetric channels. Remember, we are dealing with the symmetric channels. Asymmetric channels are much more complicated. In case of symmetric channels, y1 slash x1 is equal to y2 slash x2. Same way, z1 slash y1 is equal to z2 slash y2. All the conditional probabilities are equal for the symbols. So, we have this cascading of the two binary symmetric channels. Let us proceed. From the figure, P of z1 slash x1, see z1 slash x1 is p square into 1 minus p whole square. Z1 slash x1, just look at this. Z1 has one way like this. Z1 has one more way like this. You can see this? Let me annotate. From Z1 till x1, there is one way like this. And there is one more way like this. Okay. So it is p into p, p square. That is one path. One more is 1 minus p into 1 minus p, 1 minus p whole square. So p of z1 slash x1 is 2p square minus 2p plus 1. Now, my dear students, can you calculate the other probabilities? I am showing you p of z1 slash x1. Please tell me p of z1 slash x2. Then p of z2 slash x1. P of z2 slash x2. Just like I have shown you two paths for z1. Now you also visualize the other paths and can you give me the answer quickly? I'll give you 2 to 3 minutes time. I want you to quickly compute the other conditional probabilities and put the answer in the chat box. Okay, Kuldeep has given me one answer, 2p minus 2p squared. Chandramohan, p into 1 minus p plus p into 1 minus p. Please expand that. We want the expanded complete answer because we are going to use that later on. Kuldeep has given the answer, p of z2 slash x2 equals 2p square minus 2p plus 1. Yes, you will get that way. You will get the same answer as p of z1 slash x1. Why? Because it is a binary symmetric channel. So p of z1 slash x1 is 2p square minus 2p plus 1. Similarly, p of z2 slash x2 is also 2p square minus 2p plus 1. Let me annotate and let me show you. See, this z2 slash x2 again has got one path like this, and it has got one more path like this. So as this is a symmetric channel, both will be equal. Naturally, the other one also will be equal. P1 of z1 slash x2 and p of z2 slash x1 will also be equal. Now let me show you the path for z1 slash x2. Which path is available? This one path, 1, and then this one path, right? So it is 1 minus p into p plus p into 1 minus p, correct? In whatever way you have given the answer, that is correct. Now as this is a binary symmetric channel, even the other one is also equal, that is p of z2 slash x1, z2 slash x1, let me annotate. For z2 slash x1, this is one path, and then this is one more path. That is p into 1 minus p plus 1 minus p into p. So finally, I will show you the answers. P of z1 slash x2 is 2p minus 2p square. Similarly, p of z2 slash x1 is 2p minus 2p square. P of z2 slash x2 is 2p square minus 2p plus 1. So we have all the 4 conditional probabilities for the cascaded channel now. Please remember, this is a cascaded channel. So now just to simplify our job, let us denote this 2p minus 2p square equals q, because it is common everywhere. You can see here 2p square minus 2p and 2p minus 2p square minus 2p. So we can simply give a symbol q, naturally the other one will become minus q. If we give the symbol 2p minus 2p square equals q, then 2p square minus 2p is going to become minus q. So we can simply write 1 minus q, q, q and 1 minus q. Just for our own purpose of simplified symbolic methodology. Otherwise, when we have more and more terminologies, for the machine it is easy, for the humans it is difficult. That is why let us give the symbol. Now we can write p of z slash x as 1 minus q, 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 1 minus q, as I already told you. We can write this term as 1 minus q. This is now q, this is now q, this is now 1 minus q. Now this is going to be the noise matrix or the channel matrix for the cascaded channel. Hence the conclusion is that when two binary symmetric channels are cascaded, the resultant channel is also a binary symmetric channel but with increased error. Conclusion is that when the two binary symmetric channels are cascaded, the resultant channel is also a binary symmetric channel. How? Here we had p1 minus p, 1 minus p, p. Here also we have 1 minus q, 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 1 minus q. That means it is a symmetric channel only. So when we cascade two symmetric channels, the cascaded channel also remains symmetric as such. Again, that is also going to be obvious, right? Except for the increased noise, That is going to be obvious. But there is an increased error. Why there is an increased error? That is because we have probabilities being multiplied now, probabilities being added now. Naturally, we will have increased error. Therefore, the channel capacity is given by C of xz equals 1 minus q into Lg of 1 by 1 minus q plus q into Lg of 1 over q. Let us have a small exercise now. Two BSCs are cascaded with P equals 0.2. Find out the channel capacity. Okay. This is anyhow simple. Let me not ask you to solve it. Let me show you the answer. Two binary symmetric channels are cascaded with P equals 0.2. Find out the channel capacity. Now, given that P equals 0.2, we can directly write the value of Q. We had given the value of Q as 2P minus 2P square. So, we get 0.4 minus 0.08 is 0.32. Now, P of y slash x is 0.2, 0.8, 0.8, 0.2. Now, P of z slash x we can write directly as 0.68, 0.32, 0.32, 0.68. This was the first binary symmetric channels noise matrix. Now, this is the resultant channel noise matrix. So, now you can see that the cascaded channel is also symmetric. Let us find out the capacity. Cxy equals 1 minus 0.2 into Lg by 1 over 0.2 plus 0.8 into Lg of 1 over 0.8. That is capacity of x and y. Capacity of channel in between x and y. We obtain that as 0.278 bits per message symbol. Now let us find out the channel capacity for the cascaded one. Cxz is 1 minus 0.68 into Lg of 1 over 0.68 plus 0.32 Lg of 1 over 0.32. We get it as 0.095 bits per message symbol. You can see this. There is a drastic difference between these two. So naturally we know the capacity is going to be reduced, error is going to be increased because of the cascading. So obviously C of xz is less than C of xy. The noise is going to be having a compounding effect when it passes through two channels. So now if I have to relate it to the present communication system, here the conclusion is when we cascade two channels, naturally we will have more error at the destination. But if I have to relate it to the communication system between you and me, what is happening here? In between you and me, we have switches, we have routers, we have servers. We have so many intermediate machine elements between you and me. Now you are the destination, I am the source. In between you and me, there are so many sub parts of the channel. We don't have a single channel in between both of us. So is the error going to be this way? Let us assume that in between you and me there are so many symmetric channels only. And they are binary only, because ultimately only 0 and 1 are going between you and me. So does it mean that when we have more number of routers, more number of switches, more number of servers, we will have more errors? Someone has to answer my question. Now the conclusion is that only, right? When we have more number of intermediate machine elements, we will have more errors. Because we have seen just by cascading two symmetric channels, now we have this reduction in the capacity. So naturally when we have more number of network elements, we should have more errors, right? Someone has to tell me whether yes or no. Either unmute and tell me or put your answer in the chat box. I hope you got my question. No one is answering. Fine. The answer is no. When we have more number of switches, more number of routers, more number of servers, error is not going to increase. Why? Here we discussed only when two channels are cascaded, and we did not talk about the role of Y here. When we had Y in between X and Z, here our analysis was only as far as the channel's capacity was concerned. But if Y can detect the error and correct the error, now Y will be as good as X, right, as far as the entropy is concerned. Imagine if Y is another machine element which is intelligent, in the sense, if Y can have additional algorithm, additional program, additional resources, additional memory, additional processing, such that it will detect the error and correct the error. After correcting the error, it will transmit it to Z. In that case, how can there be error? Right now in this exercise, we did not talk about the intelligence of Y. We have not yet discussed about the intelligence of Z also. We are not yet discussing the error detecting and correcting capabilities. We are only discussing about the limitations of the channel. We are going to discuss all that in the fourth module, which is going to be quite interesting. So the point here is, when we have more number of routers and switches and servers, they are all not just general machine elements. They are all intelligent elements. They follow the 7 layers of OSI as such, right? Not all routers and switches, they are in the lower level. Whereas in my laptop, in your laptop, we have these operating systems which are working at the upper level of OSI. So that way we have physical layer, data link layer, network layer, transport layer, and all these 4 layers are driven by intelligent machines, where there is enough memory, enough speed, enough processing abilities. So that way, in the actual scenario of communication system, when the channels are cascaded, there is not going to be the compounding of errors, or there is not going to be the inclusion of more and more of errors in the cascaded channels. That is the conclusion. Okay, but there is one small limitation. Can anyone tell me what is the limitation? There is no error as such. Error will not get compounded. But what is the limitation? When we have so many intelligent machine elements in between you and me, can anybody tell me? Okay, Harshita is telling time taken to receive information is more. Very good. That is the exact answer. The answer is, when we have so many intelligent machine elements in between us, what each machine element will do is, again it will have a serial to parallel conversion, storing in the memory, applying the error detecting and correcting algorithm, then correcting the error, then again converting parallel to serial, then again it goes. So that is going to take some amount of time. Each machine element is going to introduce a certain amount of latency. Now, how can that be overcome? Harshita can give me the answer. We want to have a reduced amount of latency. What is the solution? Because as engineers, our goal is to have a faster communication. But in between you and me, if there are so many machine elements, they are going to introduce this latency or delay. How can we reduce this latency? What is the solution? Any answer? Okay, no idea. The idea is advent of VLSI. The idea is make these machines much faster. Make it as 1 gigahertz, next make it as 2 gigahertz, next make it as 4 gigahertz. That is where there is a challenge of VLSI engineers to design high-speed systems. If we design high-speed systems, then naturally all these high-speed systems will work much faster, and if the delay occurs in microseconds or nanoseconds, that will not be perceptible by the users. So as technology progresses, there is a challenge for the high-speed VLSI circuits, then ULSI circuits, then GSI circuits. VLSI will gradually move on to ULSI, ultra large scale integration, which is already in place now. Gradually it will move on to GN scale integration, and later on we may have nanotechnology. So that particular technical research is continuous as such. Continuous in the sense, the human should never experience any delay in their communications. That is the prime idea. Machines have to be made much more faster than the present machines. That is where the challenge is. That is when we have to characterize each and every MOSFET in terms of its all parasitic delays. And we will have to make logic gates work much faster than in whatever way they are working now. That is the challenge which the present VLSI engineers or chip design engineers are facing, and that challenge will remain even in future. Of course, that is not the discussion of our particular course. So for today, let me end the class. In the next class, I will be discussing one last part of this module, that is called Muruga's method. Muruga's method is going to be utilized for characterizing the asymmetric channels. Till now we have discussed only the symmetric channels. Asymmetric channels are more complicated. But one scientist called Muruga has given a solution for that. We will be seeing that in the next class. See you in the next class. Take care and bye-bye.